Hi, this is Miss Barber. Introduction to Calculus. Before we begin with new material per se, it is useful to consider the big ideas of this course. First is determining how functions are changing at a given point, and next, finding areas under a curve of a function, which is related to the total change in a function over time. These two ideas can be illustrated with some graphs. Idea 1 is illustrated to explain the derivative, a calculus concept that lets us find the rate of change of a function at a point. The graph presented. The drawing is a continuous graph on the xy plane. The graph is smooth and continuous. It is falling from the second quadrant, intersecting the negative x-axis, continues to fall, and then turns to rise. The graph intersects the negative x-axis and then the positive y-axis while rising. Then the graph turns to fall again in the first quadrant, and in so doing intersects the positive x-axis as it continues to fall indefinitely. On the positive x-axis, the points A and to the right, A plus H, are marked. Let's suppose we desire to know the rate of change of the graph at the x value of A. The algebra option is to determine another point on the graph of the function and then compute the slope of the line connecting the 2 points. This slope is called the average rate of change. With calculus, we use what is called the limit of a function to decrease the distance between A and A plus A to essentially 0. This in turn allows us to compute the instantaneous rate of change as opposed to the average rate of change. This instantaneous rate of change is the derivative at the point A. So idea 1 is intended to introduce us to the concept of the derivative. Idea 2. We have 3 graphs. The first is under the heading of what we want. The graph is an upward opening parabola that is vertically shifted up so that the vertex is on the y-axis at the ordered pair 1, 0. The region under the graph on the interval from 0 to 2 endpoints included is shaded. What we want is the exact area of the shaded region just described. Below the heading of approximation, we have the same graph as before, but with 4 shaded rectangles of equal width under the parabola and in the interval from 0 to 2 endpoints included. We observe that the 4 rectangles cover a pretty good area of the total region under the graph. It provides an approximation of the area, but with obvious missed areas in the region. And the third graph, under the heading of better approximation, has many more, much narrower rectangles approximating the same area under the parabola and on the interval 0 to 2 endpoints included. With more rectangles of much narrower width, there is much less unshaded area under the parabola than with the 4 rectangles. Hence, the more rectangles used with narrower widths yield a much better approximation. With calculus, we apply the concept of the limit, which allows us to essentially use infinitely many rectangles of essentially 0 widths to arrive at the exact area under curves such as this. So idea 2, in this branch within calculus, we call it integration. Reminders. One other thing before we begin. Let's consider exercise. Find the values of the following. For part A, 0 divided by 5. That value is 0. If you take no parts of something that is divided into 5 parts, the result is 0. Let's look at B, 5 divided by 0. This value with a 0 in the denominator is undefined. We cannot take parts of something that's not there. And finally, part C, 0 over 0. This is rather a new relationship we see in ratios. This is best thought of as indeterminate. If we look at the roots of indeterminate, it means you cannot determine. It turns out in many problems, this will depend on what is meant by each of the zeros. 1.0 Review material. Rational inequalities and sign charts. Review material on sign charts and rational inequalities. Sign properties on an interval a comma b. If f is continuous on the interval a comma b and f of x does not equal 0 for all x in that interval, then either f of x is strictly greater than 0 for all x in the interval, or f of x is strictly less than 0 for all x in that interval. The upshot of this idea is that we can use sign charts. One more definition first. Definition: a real number x is a partition number for f if f is discontinuous at x or if f of x equals 0. Steps for constructing sign charts for a function f. 1. Find the partition numbers of f. 2. Plot the partition numbers on a number line, including their values and in sequential order. 3. Select test numbers on each interval and evaluate the signs of the function for the test interval. And 4. Label your sign chart for solutions. Use a sign chart to solve the inequality x cubed is less than 4x. In order to solve an inequality, it must be set to 0. So let's re-express this as x cubed minus 4x is less than 0. Let's go ahead and name the expression f of x for x cubed minus 4x. Now we'll continue to solve. Let's factor out the greatest common factor to both x cubed and 4x, and that turns out to be x. So we'll have x times x squared minus just 4 is less than 0. The x squared minus 4 is a difference of squares, so we will factor the x squared minus 4 as x minus 2 times x plus 2 is less than 0. Now we can get the partition numbers. The partition numbers are the x values for which the function equals 0 or the function is undefined. In this case, we have 3 factors at which the function can equal 0. The first is the x. The second is if we set x minus 2 equal to 0, which solves to x equals 2, and similarly for x plus 2 set equal to 0, notice we're using the zero product property here. X would equal minus 2. Now let's set up the sign chart. We'll make a number line. And I'll mark 3 points for our 3 partition numbers in increasing order. So -2, 0, and 2. I'm going to mark above the number line as the function and below the number line as the x value. When -2 is evaluated in the function is 0. Similarly for 0 and for 2. Now we have 4 regions for which we need to evaluate the sign. So I will do so with the factor of x minus 2, and x plus 2. We have the region from -infinity to -2, the region from -2 to 0, the region from 0 to 2, and the region from 2 to positive infinity. Let's see what the sign is for x. For x, let's pick a number less than -2, any number less than -2, so -3. The sign of -3 is negative. Let's pick a number in the interval from -2 to 0, Negative 1 works. Negative 1 for x is still negative. Now let's pick a number between 0 and 2. 1 works. 1, when put in for x, is a positive number. And similarly, any number larger than 2 is also positive. Let's continue this with the factor x minus 2. Pick a number less than negative 2, like negative 3. Negative 3 minus 2 is negative 5, so that's negative. Pick a number in the interval from negative 2 to 0, like negative 1. Putting in negative 1 for the x, negative 1 minus 2 is negative 3, which is also negative. And let's pick a number between 0 and 2. 1's a good number. 1 minus 2 is a negative number. And then let's pick a number bigger than 2. Any number bigger than 2 minus 2 will be positive. And then the last factor is x plus 2. Choose a number in the interval from negative 2 to negative infinity. I'll pick negative 3. Negative 3 plus 2 is negative. Pick a number in the interval between negative 2 and 0, like negative 1. Negative 1 plus 2, well, that's 1, so the sign is positive, and because it's linear, we know that the signs don't change again. Now, let's multiply just the signs for x, x minus 2, and x plus 2. Still in the same intervals. So, negative times negative times negative in the first interval is negative. Negative times positive, well, 2 negatives is a positive. And then positive times positive, that'll be negative, and the product of 3 positives is positive. Now we are looking for the intervals where all of those 3 terms multiplied together is less than 0 or negative. So that happens in the interval from negative infinity to negative 2. And because it's strictly less than, we do not include the endpoint. And it happens again from 0 to 2. And again, we don't include the endpoints, and we'll use the union symbol to indicate that the answer to the question, where is x cubed less than 4x? Well, it happens when x is between negative infinity and negative 2, or when x is between 0 and 2. Use a sign chart to solve the inequality r of x is equal to or greater than 0 if r of x is equal to a rational expression with x minus 4 quantity squared times x minus 5 in the numerator divided by the expression x minus 1. Let's note that for this inequality, it is already factored for us, but let's write it out. So r of x is equal to or greater than 0 means the expression x minus 4 squared times x minus 5 divided by x minus 1 is equal to or greater than 0. Now we need to find the partition numbers. And let's note that partition numbers are where the function equals 0 or where the function is undefined. A function equals 0 in a rational function if the numerator is equal to 0. And so the first factor we have is x minus 4, and we'll get the partition number x equals 4. We also have x minus 5 in the numerator. Setting that equal to 0, we get x equals 5. Now we've got to pay particularly close attention to the denominator. We have a partition number at x equals 1, but x equals 1 is undefined. Let's set up the sign chart again. So I will make r of x and then draw a number line and put the partition numbers in increasing order. So we'll start with 1. Next number is 4. The next number is 5. Obviously, these are not equally spaced, but that's okay. And I'll write X below the number line to indicate those values. Since it is equal to or greater than 0, let's just keep that in mind, okay? If you put in 1 for the function, we'll write UND for undefined. 0 in the denominator is not defined. However, for both 4 and 5, those are numerator factors, and so we actually get zeros. Now let's find the sign for each of the 4 intervals. We have an interval from negative infinity to 1, from 1 to 4, 4 to 5, and 5 to infinity. Let's begin with the factor x minus 4 squared. In the first interval, pick any number less than 1, so 0. 0 minus 4 is negative 4, and when the negative 4 is squared, it's positive 16. Pick a number between 1 and 4 like 3. 3 minus 4 is negative 1, and when that negative 1 is squared, it is also positive. Let's keep in mind that any negative number squared, when squared, is going to become positive. So x minus 4 squared is positive in all 4 intervals. Now let's consider the factor x minus 5. We'll select a number in the region between negative infinity and 1. 0 is a good choice. 0 minus 5 is negative. In the interval from 1 to 4, we've got all kinds of numbers to pick. I'll pick 2. 2 minus 5 is also negative. And between 4 and 5, let's pick 4.5. 4.5 minus 5 is negative 1/2, which is negative. And you take any number bigger than 5 and subtract 5 from it, that will be positive. And we have one more factor. So let's do the denominator factor, x minus 1. 0, I'm looking at the first interval, so 0 minus 1 is negative. And then any number larger than 1, when you subtract 1 from it, will be positive. So we'll put the positive in for the remaining 3 intervals. And then let's do it all combined. So we'll have the x minus 4 squared times x minus 5, all divided by x minus 1. And what we want to do is just multiply the signs. So in the first region, we have positive times negative times negative. That's a positive. Then between 1 and 4, we have positive times positive. That'll be negative. And from 4 to 5, we got positive times positive again, which is negative. And in the last interval, 5 to infinity, it's a product of 3 positives. So that entire region, the graph will be above the x-axis, or positive. Now we need to actually answer the question, and that is, where is that function equal to or greater than 0? We have it positive in the interval from negative infinity to 1, and again in the interval from 5 to infinity. Because it is equal to or greater than, in interval notation we use the bracket to include the 5, and we'll go to infinity. Now we must be particularly careful when we look at the first interval that's from negative infinity to 1, where the function is positive, because it appears that 1 should be included because it is equal to or greater than 0. However, the number 1 cannot be included because it makes the entire function undefined. It causes the denominator to be 0, so we use the parenthesis. Negative infinity to 1, and we denote that interval with union.